Hey everyone, welcome back to Real Analysis 1. This will be lecture 3 of the course. And in this section, we're going to discuss countable and uncountable sets. Now, this will undoubtedly be something new to you unless you have taken analysis before. This is not a concept that you will have come across in any other math course. So let's go ahead and jump into it. So we'll call this section 1.3, countable and uncountable sets. Now, kind of to start, we all have, I think, an intuitive sense of what it means to say that two finite sets have the same size. Okay, so if we have two sets that are finite in order, we know what it means to say that they're the same size. So if I have A equals 2, 7, 11, 31, and if I have another set B that is 1, 2, 3, 4, then we know that just by looking at this and counting the elements in each set, we know that the size of A is equal to the size of B, which is 4 in this example. Now, we could reach the same conclusion without having to do any counting, but instead by pairing the elements off. So we could reach the same conclusion without counting by instead pairing the elements of the sets off. Right? So what I mean by that? Well, I mean 2 and 1, right? Pair those two together. And 7 and 2, sorry. Right? So pair those two together. And then, of course, 11 and 3 and 31 and 4. Right? And so we would be able to say, using this method, that A and B have the same number of elements because everything is in a pair exactly once. Okay? And so this is a kind of an alternative approach to determining whether or not two sets have the same number of elements, right? So clearly in the case of finite sets, you could just count the elements. But you could also do an operation like this sort of pairing operation. Okay. For infinite sets, the concepts of two sets being the same size is a little bit vague, okay? So for infinite sets, two sets being the same size is, I'll just say, vague, right? It's difficult to think. It's more difficult to think about. So for example, let's let S equal the set of squared natural numbers. So 1 squared, 2 squared, 3 squared, 4 squared, and so on, right? Obviously, S is infinite, right? On the one hand, we could say that S is a proper subset of the natural numbers, right? We can definitely see that, right? 1, 4, 9, 16. We're skipping a lot of natural numbers, right? But on the other hand, we could create a mapping between S and the natural numbers. We can create a mapping between S and N, kind of like what we did up here with these two finite sets. We could create a mapping very easily. So the first natural number is 1, and I'm going to map that to 1 squared. The second natural number is 2. I'm going to map that to 2 squared. 3 goes to 3 squared. 4 goes to 4 squared, right, etc. And I could continue on like this forever, right? So notice every natural number maps to precisely one element of S, right? This is what we mean by saying that we can put a set into a one-to-one correspondence. We say, so S and the natural numbers can be put into a one-to-one correspondence. Right, so even though we know that S is a proper subset of the natural numbers, clearly, there does exist a one-to-one correspondence between the two sets. All right, and so, but we would have a hard time. It's difficult to say that this set S has the same number of elements as the natural numbers, right? Simply because we know that there are things in the natural numbers, namely the number 3, for example, that isn't in S, right? S skips right over 3. It goes from 1 up to 4, up to 9, up to 16. So there's all these numbers in between the squares that are natural numbers, not in S. And yet, we can see that S can be put into this one-to-one correspondence with the natural numbers, such that every element in S maps to one and only one element in the natural numbers. Okay, so this is a great place to start in confusion, right? This sort of thing caused a lot of people to believe that quote-unquote size did not really apply to the concept of infinite sets. Okay, so I mean, you can imagine if you've got a set that is clearly a proper subset of another set, how can they possibly have the same number of elements? Well, it was Georg Cantor, a very famous mathematician, one of the most profound thinkers in all of mathematics, in my opinion. It was Cantor who really first delved into and investigated this notion of varying sizes of infinite sets. And he was the first one to really realize that this idea of a one-to-one correspondence could yield interesting results on some of the more foundational questions in set theory, right? So we will discuss this concept more, I'll say. We'll come back to this concept and what does this truly mean, what's really going on here. We'll come back to this. First, before we kind of delve headlong into this idea of countable sets and uncountable sets, we need a little bit of background. We need a little bit of set theory, and we need some definitions. Okay, so we're going to start with a definition of what does it mean for two sets to be equivalent. Okay, so two sets, A and B, are equivalent. They're equivalent or have the same cardinality would be another way of saying it, or have the same cardinality. That might be a term you're more familiar with in the context of sets. Two sets A and B are said to be equivalent, and we denote it as A is equivalent to B like this. It's a little kind of squiggly tilde. So A and B are said to be equivalent if there exists a one-to-one function, from A onto B, onto, one-to-one and onto, right? And so two sets are equivalent if there exists a one-to-one function from A onto B, and this function has to satisfy certain criteria. And so we'll say satisfying, right? The first thing is, and these are going to be the normal kind of equivalence relation type of things. A is equivalent to A, so the equivalence has to be what we call reflexive. Okay, and we need symmetry as well. So if A is equivalent to B, then B is equivalent to A. We call this symmetry. And then thirdly, transitivity, right? So if A is equivalent to B and B is equivalent to C, then A must be equivalent to C. So transitive. All right, and so we've probably seen these before, I hope, or at least you've heard of this type of this type of thing, right? So these just this is the standard kind of definition that we use for what we call equivalence relations, right? So reflexive, a set is obviously equivalent to itself. Symmetric, so if A is equivalent to B, then B is equivalent to A, right? So it kind of reverses on itself. And transitivity, if a set A is equivalent to B and B is equivalent to C, then by transitivity A must be equivalent to C as well. Okay, perfect. All right, so that's the idea of equivalence, and again, we're going to use this when we talk about two infinite sets having the same equivalence, meaning there's some kind of a function between them, which we've already alluded to in the opening here. Okay, next, let's talk. This is kind of a big definition, and we're going to come back and qualify a bunch of these things, but we're just going to lay it all out up front. We're going to lay it all out up front here. All of the different ideas about infinity are just going to be laid out here. So for each n in positive integers, otherwise known as the natural numbers, we're going to let n sub n equal 1, 2, ... up to n. Right? So this is a set. We're going to use this repeatedly throughout the course. N sub n. This is going to be a subset of the natural numbers from basically 1 up to whatever the subscript n happens to be. Right? So if n is 5, this would be the set 1, 2, 3, 4, 5. If n is 10, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If n is a million, it'd be 1, 2, 3, ... 999, 999, 1 million. Okay. So for each n in the positive integers, let's let this finite set n sub n be defined here, where I'll just say this, where n is the positive integers, I guess. Now, if A is a set, if A is some set, we say that what? Well, there's a whole bunch of things we can say here. So first of all, A is finite. It's a finite set if A can be put into a correspondence with n sub n for some n. So A is finite if there exists a mapping from a one-to-one and onto mapping from A onto this subset of the natural numbers this finite subset of the natural numbers. Or we say A is finite if it's the empty set. All right, so if A is the empty set, it's obviously finite. Okay, so that handles finite sets, right? So clearly, like the previous, the opening example of the set with 4 elements, we could easily come up with some kind of a mapping between that set and n sub 4, 1, 2, 3, 4. Okay. All right, so that's the first option. The second option, we say then that A is infinite. A is infinite if A is not finite. Okay. Now, nothing too crazy so far, right? So A is finite or A is infinite, right? These are things that we certainly would have heard about already in set theory, basic kind of set theory. Now we're going to jump. We're going to break down this concept of infinite somewhat. Okay. So A is countably infinite. A is countably infinite. Or we might just say countable. That's kind of a shorthand. A is countably infinite or countable if A is equivalent to the natural numbers. Okay, and what do we mean by this equivalent? Remember, what that means is that there's going to exist some one-to-one function from A onto the natural numbers. And the function has to be reflexive, symmetric, and transitive. Okay, so we've defined a shade of infinite called countable. Right? In order for a set to be countably infinite, there has to exist a one-to-one and onto function between your set A in this case and the natural numbers. So 1, 2, 3, 4, 5 up to infinity. Okay. Fourth, A is uncountable. It's uncountable if A is neither finite nor countable. Okay, so if A is finite, then it's just finite. Okay. If A is infinite, it can be countable or it can be uncountable. Right? If it's countable, that means there exists a one-to-one onto function from A to the natural numbers. If such a function does not exist, then we say that A is uncountable. All right. And then finally, there is this other distinction. We say that A is at most countable. At most countable if A is finite or countable. Okay, and so that's just another way. So in this case, we would say that we know that A is not uncountable, so it's at most countable. Okay, and this will come up later, later on in the lecture and other sections. So we won't worry too much about that right now, but just know that sometimes countable or finite can kind of be lumped together, and we would say at most countable. It can't be uncountable. It's at most countable. Okay, let's talk through some examples, because I mean this is can be a little hair-raising at first, all of these different shades and these subtle distinctions. So let's talk through some examples. Okay, so let's let S equal the set of squares of the natural numbers. So 1 squared, 2 squared, 3 squared, and so on. Right. Then the function, we can easily come up with a one-to-one onto function here. We would say f of n equals n squared would be an appropriate function. F of n equals n squared is a one-to-one. It's a one-to-one mapping from n onto S. Okay, right? And so the implication there is that S is equivalent to n and S is countable. Okay, so S is an infinite set, clearly, but it's also, we can now say that S is a countably infinite set. Okay. All right, so that's the example we've kind of already seen. So now we have a good working example of a weird set, S, the set of all squares of natural numbers, that is infinite. And not only is it infinite, we know that it is countably infinite, meaning there exists a one-to-one, an onto function from n onto S. Okay, so the two sets are equivalent. How about another example? Let's take a look at another one here. Let's consider this function. Consider the function, and I'll write it out here. F of n equals n over 2 and negative n minus 1 over 2. Right, and in this case, it's a piece function, obviously, so we'll say the top piece is for when n is even, and the bottom is for when n is odd. Okay, what does this function do? So what does this do? Well, let's see what happens. So let's say n equals 1. Well, n would in this case be odd, right? So we would plug it into the bottom piece. So 1 minus 1 is 0, 0 over 2 is 0, negative 0, 0. So this would take 1 and map it onto 0. What about n equals 2? Well, 2 is even, so 2 over 2 is 1. So 2 would go to 1. N equals 3. Well, 3 is odd, so it'd be this bottom one. So it'd be 3 minus 1 is 2. 2 divided by 2 is 1, and it's negative. So it would take 3 to negative 1. About n equals 4. 4 is even, so it'd be 4 over 2. 4 goes to 2. What about n equals 5? 5 is odd, so it'd be 5 minus 1 is 4. 4 divided by 2 is 2, and it's negative, so put a negative 2, and so on. You can see what's happening here. So we could prove relatively easily that f is a one-to-one function from the integers onto the natural numbers. So f is a one-to-one function from the integers onto the natural numbers. Okay, so the way we've kind of denoted it here is that we went from the natural numbers to the integers. Remember, this, if it's one-to-one and onto, then an inverse exists, and so we would have that inverse, right? So the integers can be mapped onto the natural numbers, right? And so this shows that the integers are equivalent to the natural numbers, right? And therefore, the integers are countable. Right, so they're countably infinite, as this example kind of illustrates. All right. Okay. So we've seen two sets that we would think would maybe have, that are certainly not on the surface would seem to be different sizes than the natural numbers, but in reality, when we talk about countable, they all have the same size. So the squares of the natural numbers are equivalent to the natural numbers themselves, and then what we see here is that the integers are equivalent to the natural numbers as well. We can create a one-to-one correspondence between the two sets. Okay. Now, this may surprise you, but when we increase the dimensionality, we can still retain countableness. So this theorem says that, the next theorem says that n cross n is countable. Right? So this is n cross n. Remember, this is the Cartesian product of the natural numbers and the natural numbers, right? So this would just be ordered pairs of natural numbers, right? So 1 comma 1 is in n cross n. 1 comma 2, 1,000 cross 54. 9 million cross 9,000,001, etc. Okay, so the Cartesian product of the natural numbers is a countable set also. Let's prove this one. Okay, let's prove this. So here's the function that I want to use. We'll say consider the function f of m comma n is equal to 2 to the m minus 1 times 2 times n minus 1. Okay. All right, and so in this set, using this function, we can create a one-to-one mapping between n cross n and the natural numbers. Okay, and so we'll say this function is a one-to-one mapping from n cross n to onto n. Okay, and so let's see how this works. Let's take a look. Let's dig into this. Okay, so we'll start by looking at the one-to-oneness. So let's assume that f of m comma n equals f of m prime comma n prime. And what we need to show then is that these two, m equals n prime and n equals n prime. Right, so if we assume that that's true, then we have that 2 to the m minus 1 times 2n minus 1 must be equal to 2 to the m prime minus 1 times 2n prime minus 1. Okay. Now, notice that you have the left-hand side equals the right-hand side here, and they're equal, right? So what that implies is that their prime factorization must be equal as well. So the left-hand side prime factorization must equal the right-hand side prime factorization. Right? That's just the fundamental theorem of arithmetic, right? Every natural number, or every integer, every natural number, we'll say, has a unique prime factorization, right? So if this number over here equals this number over here, then they must have the same prime factorization. Okay. So let's think about the pieces of this. So you've got 2 to the m minus 1, and you've got 2, and 2 to the m prime minus 1. So these are obviously even numbers, and their prime factorization is just a power of 2, right? This is 2 raised to some power, right? So I'll say they are certainly even, and their prime factorization is all 2. Just 2. It's just a product of 2, right? Right, so they've only got the number 2 in their factorization. Now at the same time, you've got the other piece. So you've got 2n minus 1 and 2n prime minus 1. Right, now these are odd, right? These are certainly odd numbers. You got 2 times some natural number minus 1. That's always an odd number, and same here. Right, so these are odd numbers, and so I'll say they are certainly odd, and the fact that they're odd means that they do not have 2 in their factorization. Okay, so these are both odd numbers, and they do not have 2 as part of their factorization. Okay, so then what can we conclude? Well, what we can say then is that 2 to the x times 2n minus 1 equals 2 to the y times 2n prime minus 1. That the implication here is obviously that if both of these have the same prime factorization, then they must have the same number of 2's in the prime factorization. So x equals y, right? And therefore m equals m prime. Okay. And it also follows then that n and n prime must be the same as well, since the factorizations are the same. Okay. Right? So since the odd product in the prime factorization must be equal as well, like clearly these n's and n prime have to be the same also. Right? So this shows that f of m comma n equals f of m prime comma n. This shows that if this is true, then m equals m prime, and n equals n prime. Right? Okay. All right. Okay, very good. Right, so this shows one-to-oneness. Right, so f is 1-to-1. Now, what about f being onto? What about f being onto? Right, it's not enough to show that the function's 1-to-1. We also have to show that it's onto the natural numbers. Right, f is also onto. Right, how do we show that? Well, we're going to let y be a natural number, and notice that every natural number can be expressed as a product of a power of 2 and an odd number. Right, this may be something you hadn't thought through, but every natural number can be expressed as a product of a power of 2 and an odd number. And by this I don't mean anything crazy, anything cryptic. What I mean is just this: y is equal to 2 to the k times 2p minus 1. Right, let's see an example. So 2 can be represented by k comma p equals 1 comma 1. Right, so specifically 2 is equal to 2 to the first power times 2 times 1 minus 1. So putting 1 in for k and 1 in for p. And so what do I get here? I get 2 times 2 minus 1, which is 1, right? So 2. And we'll just do one more just so you can see. So 3 can be represented by k comma p equals 0 comma 2. Right? So 3 is equal to 2 to the 0 power times 2 times 2 minus 1. So that's 1 times 4 minus 1 is 3, right, and so on. Right, so you could go on and on, like continue this. So I'm taking for granted that such a function, that you believe that such a function could actually be used to identify any natural number. Okay, and so it's just as simple then as saying letting m equal k plus 1 and n equals p, we have, if y is a natural number, then y equals 2 to the k power times 2p minus 1 is equal to 2 to the m minus 1 power times 2 to the n minus 1. Where does m and n come from? Well, m and n, of course, that's coming right out of n cross n. Right? And so, therefore, f is onto the natural numbers. I just showed that every natural number can be represented using this function, which is obviously the same function as the one that we started with, right? So what have we shown? We've shown that f of m comma n, where we set it equal to 2 to the m minus 1 times 2 to the n minus 1 is a 1 to 1 function from n cross n onto the natural numbers. Right? And so, of course, the implication is then that the natural numbers, the Cartesian product of the natural numbers is equivalent to the natural numbers, and therefore n cross n is countable. Okay, that's what we were after there. All right. So the Cartesian product of the natural numbers is a countable set, a countably infinite set. All right, very good. So we've got kind of the introduction now, right? This is all kind of introduction. What we want to do next is we want to spin up some more definitions. We're going to need the idea of a sequence, and we're going to need to talk through enumerations, and we're going to need to be able to discuss the intersection and union of sequences, and etc., all from the standpoint of countable and uncountable, right? So we'll start with this idea of a sequence. Okay. So we say if A is a set, then by a sequence in A, we mean a function f from the natural numbers into A. Okay. If A is a set, then by a sequence in A, we mean a function f from n into A. Now, for each n in n, we let x sub n equal f of n. Okay, then x sub n is called the nth term of the sequence f. Okay, it's called the nth term of the sequence f. Okay, so that's what we mean by a sequence in A. Now, we'll use different notation for this at different times. So, I mean, let's just kind of lay it all out here. So notation will frequently denote it like this. X sub n in braces like this, and n equals 1 to infinity. Or we'll use just the x of n shorthand like that. What else will we use? We'll go with that for now. I think those two. There will be other cases that come up, and I think in context it will be clear. An example here would be something like this. So if I say 1 minus negative 1 to the nth power, this denotes the sequence. This denotes the sequence f, where f of n is equal to x sub n, which would be, the individual terms would be 1 minus negative 1 to the n. Right, so that would be the nth term. Right, so for example, x1 would be 1 minus negative 1 to the first, which would just be 2. And x2 would be 1 minus negative 1 squared, which would be 0, 1 minus 1. x3 would be 1 minus negative 1 to the third power, which would again be 2. X to the fourth would be 1 minus negative 1 to the fourth power, which would be 0 again, right? And so we could say that 1 minus negative 1 to the nth power is actually just the sequence 0, 2. Okay. All right. Moving forward here. By definition, if A is a countable set, then there exists a one-to-one function f from n onto A. From the natural numbers onto A, right? And so what does that mean? Well, then A would equal the range of f, right? Which would be, we could say, is x sub n such that n is equal to 1, 2, dot, 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 the natural numbers. This sequence f is called an enumeration of the set A. It's called an enumeration of the set A. Okay. So what do I mean by that? Well, A is equal to the set of all xn such that n is equal to 1, 2, dot, 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 the natural numbers, with xn not equal to xm if n is not equal to m, right? Right, so this is what we mean by an enumeration of the set A. Right, the ability here to enumerate the elements of a countable set is going to play a very key role in the following theorem. Okay, so this is the idea, this enumeration, right? Being able to enumerate the elements of a countable set. Okay, so what is this following theorem? Well, the theorem says every infinite subset of a countable set is countable. Well, on the surface, that might seem kind of obvious, right? If I have a countable set, and I'm dealing with an infinite subset of that countable set, then it seems necessary that the subset that I'm looking at is also countable. It can't be uncountable, right? If you have an uncountable subset of a countable set, something seems amiss there, right? Because wouldn't the whole set then be uncountable if there's a portion of it that's uncountable, right? So indeed, this is somewhat logical, and you would probably have guessed this to be the case. But let's go ahead and prove it. Let's walk through the proof here. We're going to let A be a countable subset, and let's let the set x sub n, and in natural numbers, be an enumeration of A. Right, so all this is that we took all the elements of A and we listed them and labeled them in accordance with the natural numbers, right? Put them in some kind of a sequence. So let's suppose E is an infinite subset of A. We'll let E be an infinite subset of A. Then each x in E is of the form x sub k, for some k natural number, right? Right. Obviously, E is a subset of A. A we've enumerated like this, and so every x in E is going to be one of these x of n's, and so we just say so. Now we can inductively construct a function. We can construct a function f from the natural numbers to E. Okay, and how are we going to do that? Well, we're going to start by, let's let n sub 1 be the smallest possible integer, or sorry, let n sub 1 be the smallest integer, positive integer, such that, we'll let n1 be the smallest positive integer, such that x sub n1 is an element of E. Right, so E is part, we have this enumeration, right? Right, and so we just kind of go through, we start with, x sub 1, and if it's in E, then we call that x of n sub 1. If not, we go to the x sub 2. We just keep kind of moving through this enumeration until we find the first element that's in E. Okay. Right, so let n1 be the smallest positive integer such that x of n1 is in E. Right, and then we could do the same thing. Let's let n sub 2 be the next smallest, and so on. Okay, so we've chosen n sub 1, n sub 2, dot, 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 n sub k minus 1, such that x of n sub 1, x of n sub 2, x of n sub 3, dot, 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 x of n sub k minus 1. These are all elements of E, right? And we've just sequentially pulled them out of this enumeration. Okay. Well, how do we pick the next element? Well, we'll let n sub k be the smallest integer. Let n sub k be the smallest integer greater than n sub k minus 1, such that x of n sub k is in E, but it's got to be in E when all of these are removed. Okay, so it's, just moving forward in the enumeration. Okay. right? And so you can see that this naturally creates this function where basically we set f sub k equal to x of n sub k, right? Are we ever going to run out of k's? No, of course not. E is an infinite subset, right? A is an infinite, it's a countably infinite set. E is an infinite subset of A, right? And so we just keep going to the next element, right? We just keep moving through it. We'll never exhaust the elements, but we'll get them all eventually, won't we? Okay. Okay, so let's kind of formalize that piece of the argument, right? So what do we mean here? Well, since E is infinite, f is defined for all n in n, right? So there is going to be a 1,000,001 element for E, right? So we could just keep going forever and ever, right? E is an infinite subset, right? And then we can also say that if m is greater than k, then if m is greater than k, then n sub m will be greater than n sub k. And therefore, we can see that f will be 1 to 1 because x of n sub m will be, well, not equal to, we could see here it's greater than, it'll be not equal to x of n sub k. Okay, so f is 1 to 1. Okay, so f is 1 to 1. The onto question, f is obviously onto E, since if x is in E, then it's equal to, x is equal to some xj, right? So if x is in E, then x equals x sub j for some j and n. Right, and so by construction, f is onto n. Okay. And that's basically what we need, isn't it? Right? That's basically what we need. If you start with a countable set, then it's, and you've got some infinite subset of a countable set, then there's always a way to map that infinite subset to the natural numbers, just using this kind of enumeration concept. So any infinite subset of a countable set can be mapped to n using this trick with the enumeration. Okay, therefore, any infinite subset of a countable set is countable, right? Because it can be mapped to n. Right, so that's the proof. Again, that was a little bit conversational in that proof. You could spend some time to formalize some of those pieces. My goal here is just to kind of get the idea across. Okay. All right, very good. Very good. Let's see. We'll push on a little further. This will be a longer lecture. That's okay, though. We're used to these long lectures from analysis. It's going to be a recurring thing. So, the next theorem. Let's see, what have we got next here? Okay, the next one says that if f maps the natural numbers onto A, then A is at most countable. Okay, so if I can come up with a function that maps the natural numbers onto my set A, then my set A could be finite. It is possible to do that. We just saw an example earlier of that. But it could also be infinite. And if it's infinite, it's at most countable, right? So namely, if I can come up with a function that maps n onto A, then A cannot be uncountable. It has to be countable at that point. Okay, so that's the idea with this theorem. Okay, and we'll use this a little bit later. I'm going to skip the proof for this, but you could easily go and look this one up, or you could try to prove it yourself. I think you might be able to prove it yourself. It depends on who you are. But the proof is not terrible. It's not terribly difficult, but we'll skip in the interest of time here. Right, but just keep this in mind that this, and I think this is somewhat intuitive. This isn't too much of a stretch. Like if you can find a mapping from the natural numbers onto your set, then your set can't be an uncountably infinite set. Right? There's no way to take the natural numbers and map them onto an uncountably infinite set. It sort of goes against the whole idea of a countable set, right? Right. So your set is at most countable. It could be finite even. It is possible. Okay. Very good. Very good. Okay, another definition here. We're going to talk next about we need to be able to discuss subsets and families of subsets of an infinite set with a little more. We're going to need a little more rigor, and so that's kind of the point of this next section, is introduce a bit more rigor around the idea of subsets and families of subsets. So let's let A and X be non-empty sets. So we'll let A and X be non-empty sets. Then an indexed family of subsets of X with index set A, okay, is a function from A, the index set, into the power set of X. Okay. Okay, that's what we mean by an indexed family, right? So remember what the power set of X is. The power set of X is the set of all subsets of X, right? And so an indexed family of subsets is a function from your index set into the power set, right? So let's break this down. So if F is a function from A into the power set of A, then for each alpha in A, we let E sub alpha equal F of alpha. Okay. Okay, I think I mean X here. Sorry about that. Okay, so if F is a function from A into the power set of X, then for each alpha in A, we let E sub alpha equal F of alpha. Now, as for sequences, we denote this function. We denote the function by, the same kind of notation, E sub alpha, such that alpha is in A. This is very similar to what we did for sequences. Right, and so frequently, if A is like the natural numbers, you may see this notation. We may write E sub n such that n is a natural number. Right, or it's possible we might write e sub n equals 1 to infinity, that kind of thing. Okay, just these all kind of mean the same thing. Okay, let's see an example here. This can be a little awkward at first, but it's all fairly straightforward actually, but it's some of the notation and the description of what these things mean can be a little bit challenging at first. I recognize that. So let's say the sequence n sub n such that n equals 1 to infinity, where n sub n, remember that, is 1, 2, dot, 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 n. This is going to be a sequence of subsets of the natural numbers. Okay, what is this sequence? Well, the sequence looks like this, right? It's 1, right? That's 1 sub 1. N sub 1 is just 1. And then n sub 2 would be 1 and 2. And then n sub 3 would be 1, 2, 3, so forth. And then what would you have? 1, 2, 3, dot, 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 n, right? And so forth. Right? So this is the function from n into the power set of the natural numbers, isn't it? Right, that's what's happening here. Okay. All right. Very good. Let's do another example here. Let's say for each natural number n, we're going to set I sub n equal to the set of real numbers x and r such that 0 is less than x and less than 1 over n. Okay. Then this isn't going to be a sequence of subsets of the real numbers, right? So we could say I sub n such that n equals 1 to infinity is a sequence of subsets of the real numbers, right? These are all the real numbers between 0 and 1 over n, right? So depending on n, I can create a sequence of subsets here. Okay, very good. Let's do another example. Well, one more example, and then we'll move forward here. This will all kind of come together in a moment. So for this example, let's say for each x, we're going to let e sub x equal the set of rational numbers r and q such that 0 is less than or equal to r less than x. Okay, and so in here we'll say that x is limited between, x has to be between 0 and 1. We'll say 0 is less than x less than 1. Right, so we'll limit our index set to just this interval. Okay. Then we could say that e sub x such that x is in 0 to 1 is an indexed family. It's an indexed family of subsets of the rational numbers. Now our index set here is an open interval, right? It's the open interval 0 to 1. All right. Very good. Okay, now what can we do with these things? We can do lots of really cool stuff with these things, actually. But I think we'll pick this up in the next section, or in the next lecture, in part 2 of this lecture. Sorry. Just in the interest of time, let's kind of break the videos up logically here. I think this would be a good place to break, and then we'll come back and probably have about another hour or so of discussion in part B. So we'll see you in a moment in part B.